and that will be routed through these switches and routers. So in routers, for example, this packet will be unpacked. So for example, it will look at the frame layer header and then make it into a datagram. Then in the datagram, the router will decide where to forward this datagram to. And before it forwards it, encapsulate it again in another new link layer header. Then that becomes a frame. This frame just keep forwarded to the destination. Once this packet arrives destination, basically this host will need to do the reverse of this encapsulation. It takes away all these headers until it delivers the message to the application. So here, each of this packet has a payload and a header. So last time, remember, we used the analogy between one person to send a letter to another person in another campus of OU. So encapsulation is like putting a message inside an envelope, inside another envelope. So if you are in a semester-long computer network course, usually you will just go through this product stack layer by layer. So first they will cover application layer, then transport layer, then network layer. But since in this course, we only have time to give you a very brief introduction. So in the next two chapters, we'll only have time to cover the application layer and the transport layer. So in the application layer, we'll teach you how to do some basic network application development. And then you will use the software programming. So in the next layer of the net transport layer, we'll explain you some basic, the mechanism behind the message transportation that happens in the transport layer. Okay, so this is chapter 2. We will first talk about the principle of network applications. We covered the beginning of this chapter a little bit in the last lecture. Basically, there are many examples of network application, like emails, web, text messaging. This all uses the open protocols, and there are also a lot of proprietary protocols like voice over IP, social networking. There are basically two steps that you can do to develop a network application. So first, you need to write a application to run on the server side, like this run on the data centers. Also need to write an application to run on the client side. Then the nice thing about this product stack is you don't need to worry about the details of the message transmission. So basically the client side just pushes a message into the socket. Then this message will naturally transport it over the internet and pop out the other end. So this is a way for this protocol stack to abstract away all the complexity. So basically the message is transported from process to the next process between the two hosts. When you try to develop a network application, so there are basically two architectures to use. One is client-server architecture, the other one is peer-to-peer architecture. So we'll go over this a little bit. This is the most commonly used architecture. First you have a server. So this server is always on. It just waits for the client to be contacted. And it has a permanent IP address. Typically they sit in a data center. So the way to think about it is server is like a restaurant, for example, like Chick-fil-A. It waits for the customer to come in. It must have a permanent IP address, just like any restaurant. It has a physical address, so the customer can know where to find this restaurant for service. On the client side, it's maybe intermittently connected. So it's like your cell phone. You may go to Facebook on one app, then you disconnect. You may go to the WhatsApp to the next. So basically it's intermittently connected. And then you have dynamic IP address. So this is like you go to like a Chick-fil-A. So basically you pop in, you get a place order and get your sandwich, then you leave. And the clients doesn't really communicate with each other. So this is always a transaction between servers and clients. So besides this, so I think the most common examples of this kind of server mode is web browsing. So you use a web browser like a Safari or Firefox, and you contact a web server. So you can get rid of some other application you use that uses this client server architecture. I'm sorry?
Video games?
Google Video Game, yes, that's a good example. Yes. So most of the apps on your phone uses this kind of client server mode, like Facebook. You are sending data to Facebook servers. This is actually a more interesting architecture that's the peer-to-peer architecture. So this basically all the hosts in the peer they are a peer. So there's no central server here, but in fact every host here is both a host, is both a server and a client. So basically, all this peer hosts can communicate with each other. So the biggest advantage is self-scalable. Each peer basically can get a service from other peers. So let me give you one example. Let's say you have a big file, like a movie, a 4K movie, like terabytes of size. And you need to distribute this movie to as many clients, as many customers as you can. So I can do a server client mode. That means I'm the server. And let's say you have 100 clients who needs this movie. They basically need to copy this 100 gigabyte of file, one by one, right? So basically the complexity is the n. So alternatively, what I can do is I can pass the file, I can copy the transfer file for the first client. Then ask the first host to keep copying this movie to other hosts. So this is like a virus transmission. Basically, every new users who got the file can serve as the new server and to distribute the files. So as you can think, this is basically a log-n complexity, right? So basically, it's all these new clients who got the file can become a server. So in this design, because there's no central server, there's no single point of failure. And it's very scalable. You can think of some examples of applications that uses the P2P architecture. I'm sorry?
Nintendo video game.
I don't know about that.
BitTorrent.
Yes, that's a good example. So in BitTorrent, that's exactly what I was talking about. So it's very scalable. Actually, there's no central server for you to download. So this is why it's very hard for the governments to take it down. If you want to sue someone, there's no one particularly can sue. Can you think of other applications that use P2P architecture?
Stuff that lets you remote into other people.
In that case, a remote computer will be your server. So the other example is, yeah.
There's some messaging apps, but
Yes, Skype. Skype is the only example. So when it's invented by some guy in their garage, they cannot afford big servers. So basically, they let them video message pass between different hosts, and that becomes a P2P service. So another example is Bitcoins. So there's no central server to give you Bitcoins. Basically, it's all the hosts that themselves communicate with each other and decide how to do the record keeping. So you can see this P2P architecture is very resilient. So if you are afraid of the man to shut you down, so this is the architecture to use. But if you want to make money, you use this kind of server.
Skype still through there?
Not anymore. So Microsoft changed it to this architecture. It's more stable. Okay, so now let's say you want to develop a network application and you decided to use either a P2P architecture or a client-server architecture, then how do you actually develop it? In the network programming, the entities that are actually sending messages back and forth are actually the processes. So basically, the process is a program running within a host. I think all of you guys have taken OS, so you should know what is a process. Within a host, the same host, actually two processes can also communicate with each other with a special IP address. And in this example we're going to cover in this lecture, and in your homework, we'll ask you to do the test within using only your laptop. So this is a very nice way to debug your code. So of course, when you're communicating between two processes, you use this internet protocol stack. Actually, it doesn't matter which process is sitting where. So the process you are communicating may be sitting on the same laptop as you are using, or it may be sitting in around the globe, like in Asia or Africa. When you're doing the communication, process communication, and if you use the client server architecture. So basically, you are trying to write a client program that starts this client process, and also you are writing a server program that runs the server process. Okay, so now we're going to get into the next concept, the sockets. As we mentioned last time, in the Internet protocol, every computer, every device in the net is identified by a unique identifier. That's called an IP address. So here we mentioned that the communication actually happens between two processes. A host, a computer can have multiple processes running on it. So there should be some way when a message is delivered to this host by its IP address, we have to still need to identify which process actually needs to receive this message, right? So this is to go through this socket. So basically, we identify a process through a port number, and then this port number is associated with a socket. So we can think about a socket as a door. Process basically pushes this message through this door. So you can actually think about it pushes the message down this protocol stack. Then all this is taken care of for you to go through the next few layers by the operating system, also the routers along the way. On the receiving side, actually, the receiver also receives messages through the socket. So you can think about this is a door. Basically, this process just waits for something to pop through the door and it just receives this message. So as we mentioned that a host device, all the host device has an IP address. Currently in the IP version 4, it uses a 32-bit IP address. All the hosts in the internet must have a unique IP address. So let me ask you, if you use a 32-bit for the IP address, how many hosts can you have on internet? 2 to the power of 32, right? Or something. So that is correct. So when the internet is invented in the 80s, that's a very large number, astronomical number. But now actually that's not enough. In the next version of IP protocol, IPv6, they actually used 128 bits. So basically you will be able to host 2 to the power 128. So that number of IP addresses can be assigned to every single grain of sand on Earth. So that should last for a while. So now this will solve the problem of identifying a host. Now how do we identify the process? Because we have many processes running on a host, right? We kind of jump. So that's through this port number. So there are a lot of protocols that uses some very well-known protocols. Like if you use HTTP, it always uses port 80. If you use email, it always use port number 25. That means in the host, in the server, there's a server process that's running. And that server process, if it's handling HTTP request, is always listening to this port 80. So for example, if you want to send a HTTP message to some web server, you have to specify what's the IP address of that server, and the port number should be 80. So we'll talk about this in more details when we actually work on the socket programming. So we are trying to exchange the message between a server and a client. So usually you have to define a format for the message. Like I can say something to you in some arbitrary language, you will not be able to understand it. So just like in any other application protocols, you have to define the syntax. So typically the message you define how do you request for files and how do you respond to those requests. And then within this message, you define what fields do you provide and how do you delimit those fields and the syntax and the semantics of the message. One thing you need to remember is there's only 2 types of protocol. One is open protocol, like HTTP. That means everyone agrees on the standard. On the client side, you can see that as long as you have a standard, you can have multiple implementation of that client program. For example, with HTTP, there's a Firefox browser, Safari browser, Chrome browser. This is because they all implement to some open standard. And on the server side, there are also all kinds of different server programs, and there's also developed for that open standard. At the same time, that means it's very hard to evolve that standard because this is a process that has to be driven by consensus of the community. So if you are Facebook and you want to develop some other protocols, you can always invent your own proprietary protocols. So basically you get to define how the message look like. In your homework, we ask you to do a socket, do a client-server communication program. In that case, we'll also ask you to define your own message format, which is specified in the homework. So let's say we have defined this message. We have decided, okay, the client and the server can communicate in this format. Then we actually send a message over the network. We actually need to expect some kind of guarantee of service from the network service, just like when you send a message over the postal mail service or send it over FedEx, you are expecting some kind of guarantee of service. So here, there are actually four types of criteria we use. So first, the data integrity. That means if I send a message over the network, can I expect this message will be delivered at all? Can I expect the message to be delivered without any corruption, without any error? So this is called a reliable service. For some application like file transfer or web transaction require 100% reliability. That means if I send you a file and one byte is corrupted, it's most likely that file cannot be opened anymore. Or some other application can tolerate loss, like a video. If some byte gets lost, it just means you have a glitch in your video, so that can be tolerated. The second thing is the timing. Can you guarantee this packet will be delivered in time? In emails, that's not a critical issue. A few seconds of delay doesn't matter much. But if you're doing a video transmission, then that is a very important criteria. Throughput, then that means what's the transmission rate you can guarantee from using this service. Can you guarantee like transmitting 100 bits per second? And then finally, security. If you send a message to another process, can you have the confidence that no one can look at this message? You have the privacy. So if you look at this, this is actually very similar to if you use FedEx or USPS. Can you expect the FedEx to deliver a package to this person intact? Can you guarantee that if you bought a overnight shipping, can you expect the package delivered in the next day? And how many packages can you send to this FedEx sorting facility at a time? And finally, can you guarantee that FedEx will not let anyone else look into the content of your package? So now, this is a few common applications, and this is some common criteria. Do they expect this kind of guarantee of services? For file transfer, it needs no loss. It cannot tolerate any loss. But the throughput is elastic. You can wait for a few more minutes. It's not a problem. It's not time sensitive. But for video applications, it's kind of in the opposite. They can tolerate the losses, but it needs a certain minimum throughput. For video, it tends to require at least 10 kilobits per second. And it's time sensitive. If you don't want to experience lags from watching a TV, you need a time sensitive application. Then there's a few other examples. So let's say you have defined your application. You know whether it can tolerate loss, whether it can tolerate a delay. So then you can choose two services provided by the internet. So one is called TCP, the other one is called UDP. And this is their pros and cons. So TCP first will guarantee you a reliable service between the two processes. So that means when you send in 10 packages from a source to destination, TCP will guarantee you every single one of them will be delivered, and they will be delivered without error, and they will be delivered in order of their sending. So if you remember in the first chapter we talked about, when you're transmitting a packet over the network, if there's a congestion, some packet get lost, right? So remember that. And how do you guarantee a reliable transport service on top of a network that may lose some package? So this is a topic we'll cover extensively in the next chapter, is how do you build a reliable service on top of an unreliable network. Then it also provides flow control and congestion control. So this is being very constricted to other users of the internet. For example, if it sees receiver is being overwhelmed with incoming message, the TCP service actually will tell the sender to throttle down your rate of transmission. So this is only about the receivers being overwhelmed by the incoming message. And this congestion is over the network. So that means if a TCP service senses a congestion somewhere over the network, it will also ask the sender to throttle down its transmission. So this avoids congestion in the network. So of course, this will deteriorate the service provided to this particular two pairs of processes, but it makes the whole network communicate more smoothly. But still, it doesn't provide any guarantee to the timing and the throughput or security. And it also requires some setup. So we will talk about this in detail when we cover the socket programming. On the other hand, this UDP is basically a bare bones service. It doesn't provide any guarantee. So basically, it doesn't provide any reliable data service. Basically, you can send a message using the UDP. Then UDP mail may not be able to deliver it. And the mail may not deliver it in uncorrupted form. And of course, it doesn't provide the other things too, like flow control and congestion control. Basically, the message will be just jammed into this socket. Then it doesn't matter if the network can handle them or not. So it sounds like this is overall a better service than the UDP. Then why do we need a UDP? Sorry? Speed? Yes, that's one reason. Any other? So when you're getting all this advantage you get from TCP, there are some disadvantages. So none of this is free for you. So for example, as we mentioned, to achieve reliable service, that means when there's a packet that got corrupted, the packet needs to be resent. When message is actually delivered out of order, again, those messages need to be resent in the order. So that means you have a delay in the transmission. And also when you are being considered to other people, you do the congestion control. That means your own share of the network bandwidth is reduced because you are letting the bandwidth, you're giving out bandwidth to other applications. But the UDP doesn't care any of those. They shove the message out the door. We talk about these applications, and this is the protocol they use. As we mentioned that emails or web, they all require a reliable transmission. So that's why they all chose the TCP protocol. But for streaming multimedia, like when you're watching YouTube, they probably use the UDP. And if you use internet or telephone, they also probably use the UDP. The primary reason is they don't care about the packet loss, and they require as much bandwidth as they can get from the network. So when you develop your application, this is another choice, design choice you have to make. Do you choose to use UDP or do you choose to use TCP? And then in the next chapter, we'll talk about the mechanism behind their service. Okay, so we covered the principle behind this network application. So let's go to in-class exercise 1.2.1. So as you can see, I experimented a different format. So now the exercises are not protected by passcode anymore. So if you need to review them before the class, feel free to do that. So for this exercise, I'll just give you 5 minutes to think about this. So if you have a question, feel free to ask me or talk with the student next to you. Okay, so let's go with the problems together. So first, it asks you about what kind of services you can expect from a transport layer protocol. Usually, I think about this like how you expect what do you expect from FedEx? It has to provide a reliable data transfer, which that guarantees the packets will be delivered without error in the right order. TCP provides that, and the UTP doesn't. The throughput, that means can guarantee a certain rate of transmission. So neither one of them actually provide that. In fact, TCP may degrade this to avoid a network congestion. The timing, that means how much delay can you expect. Then again, TCP and UTP doesn't provide that. And also confidentiality, can you expect any privacy in the message? So neither one actually provides that. But of course, you can still provide this kind of encryption in your application. For example, if you send a message, the message may be encrypted in some fashion. Then how do you tell which process is the client and which process is server? So servers tend to be on already. Like if you go to a restaurant, it should be always on, and it has a fixed address, so all the clients know where to go to get the service. So this is the opposite for clients. Basically, they request service from the client. They may have a intermediate connection, and they have a dynamic IP address. Questions about this? Then how do you identify a process to communicate? So first you have IP address. The second, you need a port number. So for example, if this host needs to send a message to this process, it first needs to identify this host by its IP address. Then when this message is delivered to this host, then this host will look at the port number and send the message to the correct process based on its port number. So here actually I gave you until the end of the day to submit the answer. And then I will upload the solution tomorrow. So if you need a bit more time to think about this, feel free to do that after the class. Submit your answer by tomorrow. Okay. Okay, let's continue with the next section of this chapter. Okay, in this section, we're going to work on some actual code for network programming. So first, we'll learn to use some basic client and server application. Here this is called a socket programming because we will be communicating between processes through the sockets. In this section, we're actually going to use Python to do the socket programming. socket programming are also available in Java or C. So all this language provides libraries, provide this kind of socket programming interfaces. So here we use Python because that's more clear to look at and more clear to write. Of course, it doesn't apply a lot of low-level control over the communication. Just to remind you, we can use two types of transport services. One is called UDP, the other one is TCP. With UDP, you get an unreliable service. So look at this, it actually transmits a package that's called a datagram. So if you remember, datagram is also the name we gave to the packet in the link layer. So unfortunately, this is a collision in the namespace. So here, all this message that's sent by UDP is also called a datagram. So to avoid confusion, I'll try to call all these messages called UDP messages. For TCP, it provides a reliable byte stream oriented service. That means all this, you will need a connection, establish between two processes before you can communicate. So here we're gonna develop this application. So it's pretty simple. We have an application process that reads a long character from the keyboard and send this line to the server. The server will receive this message, then convert all the character to uppercase, then sends this new string back to the client. Then client receives the message that displays the line on the screen. So you can see there are two communication processes here. One is the client needs to send the message to the server sends the message back to the client. And it will show the implementation both with the UDP and the TCP. So this is another explanation of UDP from the perspective of a socket programmer. So first, UDP has no connection between client and server. There is no handshake before sending data. What that means is if I'm a process and I need to send a message to another process, I just need to know the IP address and the port number, and then I will start to send the package. So like if I'm the client, one process and you communicate with one of you, I just show up here and tell you you're awesome, then I just walk away. Actually, he would not be able to prepare for that, and I don't even know if he gets my message. So this is what we call there's no handshake beforehand. Alternatively, if for TCP, I may come to you, I may communicate with you, I may say, hello? Okay, I can see him not. Then that means, hey, I got your attention, then you're ready. Then I can tell you what's the time, so you can respond back. So we can have a communication, we can have a connection before you do communication, right? So you can see the difference between the UDP and the TCP, right? So here, the sender just need to find the IP address and the port number, then just send the data away. And then receiver can know who sent the data, basically the message, and actually attaches the IP address and the port number. And of course, as a sender or receiver, you never know if the packet you received is uncorrupted or delivered in order. And sender doesn't even know if the message has been delivered or not. Okay, so let's see how we can implement the application. So remember, we have to send a string back and forth between two processes. So first, on the server side, it needs to create a socket first. That means, remember, so communication occurs through the socket. Socket is the door that you push the message out. So like say, first you ask the operating system, give me a door. So this is the command. On the client side, you also need to ask the operating system to create a socket. Then after it creates a socket, then it can create this datagram or the UDP message. Then push that message out through this socket. Then somehow the message will show up on this server side. Then the server will read this datagram, this UDP message. Then, as we mentioned before, we will convert this message to uppercase. Then we have this new string. The new string will be sent back to the client, and the client will receive this message and display it on the screen. So this is the actual code. I already uploaded the code to the canvas. If you go to the file under section 1, you will see a file called udpclient.py. And This is an example we'll use for in-class exercises. You should also follow this example for your homework. Here, we'll just go over this program line by line. So first, you got to import this library called the socket. So this is a Python. So if you use Java or C, they all have their own version of this socket programming library. Then in the next line, we'll create this socket, this UDP socket. So first, you probably need to get familiar with Python. So here, we're just creating two strings. The first string, we call it a server name. The second string, we call it a port number. We just give it an IP address for the server. So I mentioned before, for this host itself, it has a special IP address. So this IP address is 127.0.0.1. So basically, that means if you send a message to this IP address, it will be delivered to the same host. And since in this example, we want you to be able to test the server and the client on the same computer as your laptop. So this is why we use this server IP address. Port number, we just up here gave it a number, 12,000. So remember, the port number below 1,000 are typically assigned to some open protocol like HTTP use port 80. So if you use port 80, there will be some conflict. But if you choose a port number above 1,000, usually you should not have any conflict. So here we just arbitrarily designate 12,000 as our port number that's associated with this client process. Sorry, that's the port number for the server that you're going to communicate with. On the server side, we'll designate this port number.
How large can the server port number be?
Typically it's below 100,000. Right, but this, I think you probably should look at the implementation to know the maximum number. Like this Python implementation. Next, we'll create this socket. So here you can see that we have this socket method that has take two arguments. The first argument means it uses the internet protocol here. So in this course, we're only going to cover internet protocol, so we can always use this constant. Then the next parameter, it asks the library to give it a UDP port, UDP socket. So here you can see this dgram, that's standing for datagram. So it needs a datagram socket, which is UDP. And after this, the return of this method will give you this kind of socket. So next, we'll get the message. So this is basically a command for the Python to get a user input from the command line. It will print out a message, input a 8-word character sentence. Then whatever user input in the command line will be put into this message stream. So now, here is the actual standard action. So first you can see this is an object or a kind of socket. So that's created here. And the send to is the command to send a message. This message here is the string you just got from the user. Then this encode means it will convert this from a string to bytes. So this virtual bytes actually will be transmitted down the socket, down to the next layer. And then here, you have a server name and a server port. So that's defined here. So you can see that put into a parenthesis. If you are not familiar with Python, you can put a multiple variable inside the parenthesis. That means they are packed into a tuple. So here, this the destination is specified as a tuple for two variables. The first one is the IP address of the server. The second one is the port number of the process of the server. Okay, so now you can see that here we have a socket. That means we have a door, and we have a message, and we attach a destination address and a port number. Then this will be sent out. So basically, this is the end of the client program. So somehow the message will be delivered by the server. And the server will do something about it. So in this particular case, the client actually is expecting some reply from the server. So this is the receive. So here we can see that we actually didn't say receive from what server. We didn't need to do that. We just take this, look at this socket. So that means we have a door here. Before we are the client, we just watch for this door, watch for things to come in. We actually don't know who's going to send that message. And this number, 2048, that means the buffer number. So that specifies what's the maximum length of message we will be expecting. If the message length is shorter than this number, like if you have a message of 1,000 bytes in length, then only this 1,000 bytes will be delivered to this return here, the modified message. However, if the sender have sent a message longer than this, like say you have someone send this kind of 3,000 byte message, then only the first 2048 byte will be delivered, so it will be truncated here.
Is it optional or necessary?
You have to specify this.
What if you don't know the size of the message? How do we take into account that?
That's one of the disadvantages of UDP. So you actually need to specify a very large number to make sure the message doesn't get truncated. If you really need to, if you really don't know the message size, you should use TCP to do that. So if you have control of the server side, you can always break the message down to multiple messages, right? If you have control of the server side. Okay, so the return value is a tuple. So if you're not familiar with Python, it returns a tuple which contains two values. The first value is the message itself. The second value is the address of the server. So basically, you got a message coming in. You can actually look at this message, look at it, and then know what's the IP address and what's the port number of the process sending this message. That will be put into here. Okay, we have the modified message. Then again, this is in bytes. We actually need to decode that into a string. So we just call .decode, and this can be printed out. Okay, now this client has finished this transaction. Now it can be closed. So this is a UDP client program. Any question about this?
Why the encode and decode? I mean, it's still bytes even before you encoded it, right? How is it changing the representation as a string?
Right, so for the Python, it uses a string, right? So like in Python 2, it uses ASCII, in Python 3, it uses Unicode. So I assume somehow the Python will do some decoding here. So this message can also be like a number. It also need to be encoded by in bytes.
The Python string representation is a derivative from an object directly, so it's not just the bytes. That's why you need to encode and decode.
Additional information.
Yeah.
Thanks. Okay, so this is the server side of the UDP program. So here, similarly, we call this command. You specify this is an internet protocol, and you ask for a UDP socket, and that's the same command you can create on the server side. The one thing that's different is on the client side, you can see that we actually didn't specify a port number. Basically, this port number is assigned by the operating system. But on the server side, we should specify a port number so that the client know where to send the message to, right? So here we just use this command, this bind command. So this is actually two single quote comma, so not a single double quote. And then we give it the port number, so that's 12,000 here. So basically this will bind this port number to this socket. So that's how we know we specify the 12,000 in the client program. So this is a prior knowledge you have to make sure the client server know beforehand. After you bind, then assign a port number to this server socket, then you can print a message to say that server is ready to receive. Then we have a while loop. So you can see this is an infinite while loop, right? So what the server does is just waiting here for the server to be for the client to contact itself. So this is called a busy wait style. And every time in every loop, it will actually try to receive something from the socket. So again, we have a buffer size of 2048. whatever that's received from this socket will be passed to these two return value here. One is the message itself, the other one is the client address. So this is basically the same as the client side. Then after we receive the message, it will be decoded into string, then turned into uppercase, then assigned to this modified message. And this message is sent back to this client. So it's the same thing as the client side. You specify a socket, so that's what you created here. And for the client address, we captured it here. So when you receive a message from the server socket, you save it here. But in the client side, actually, we explicitly use the tuple to specify the address to send the message to. Okay. Any question about this UTP server program?
So it sends it with the client socket that's sent to, and then we receive like the third last line on the client is just receiving what the server's done in the socket. Am I understanding that correctly?
Yes. In this particular implementation, it just waits here. So this is a blocking command. Okay, so let's contrast it with TCP. In TCP, it's a connection based. That means the client contacts the server. They do a three-way handshake. Then after the three-way handshake, they actually have a connection between them. Then they can just communicate through this connection directly. You actually don't need to specify the destination when you are using this connection. We'll cover a lot of this detail in chapter 3. Here you probably need to, the key thing to remember is the server TCP creates a new socket for every kind of process. So you can think about this way: is if you go to DMV, typically what you go to a front desk, you get a number. Then once you have that number, then the DMV will create a window for you. So that's a connection. You go to that window to communicate. So let's look at how the connection. So first, on the server side, again, you create a socket. So of course, here we are going to create a TCP socket. Then we just wait for the incoming connection request. On the client side, we also create a socket. Then they can build a connection. So this means they know what the opposite side's IP address and the port number. And then this client will send a message to the server. The server receives the message from the connection socket, then writes a reply to this socket, then reads the reply, then calls the connection. So the key difference between the TCP and the UDP is this connection step in here. So UDP doesn't need to do this. So now let's look at the code. So first, similarly, in the TCP client, you need to import this socket library. Then we specify a server name. So here we just use a generic one, but in your example, we actually use the same 127.0.0.1 as the IP address of the server. And here we also use 12,000 as the port number. So here we also use Internet protocol. But since we need a TCP connection, we specify as a socket stream. So TCP is also called a stream-based socket. So this is why it has a string here. So now this will return you a TCP socket on the client side. Then the client can connect with the server. So remember, we don't need to do this in the UDP side. We just throw a message at this server by the IP address and the port number. But here we have to first do a connection. So this is a three-way handshake. Remember, we had to do the hello to the client and then receive the response back, then start a connection. So again, notice that we have two parentheses here. The inside parenthesis just pack these two variables into a tuple. Then we read a sentence from the user. Then we send this sentence to this socket. So you can see that when we send the message here, we actually didn't specify the destination, right? So that's because when we created this socket, what it did connected with this server socket now. So when we have next time when we use send message into this socket, we just need to specify the message. So here after we send, then also this is the receive side. We also here we actually don't need to specify what's the receive from. So we just say receive. This is a buffer. It's a 1028, but this is a bit different from the UDP. UDP sends messages one by one, but the TCP receives strings. That means this is actually just a temporary hold. That means this socket will receive 1024 bytes from this connection and pass it here. If there are more, you can recall this command again. It will deliver the next set of bytes, 1024 bytes. So this basically the operating system will hold that in the buffer for you. You don't need to specify a maximum number. So that answers your question if you don't know that. So you can specify a loop here. You can keep receiving the next batch of 1024 bytes. So once we receive this modified sentence, we can print out, then we close the socket.
Does the operating system determine the size of that buffer? And do you reasonably change that?
Probably there's some way to do that. It's probably going to be a very, very big number. So usually when you do the TC socket programming, you don't have control of that. So this is what you can control. In the exercise, you can see that we did an implementation with value, so you can keep receiving more next set of bytes from the string. In the exercise, we'll see that. Okay, so this is the server side of the application. Similarly, we specify the port number is 12,000. Then on the server side, we'll create a socket. So again, you can see socket string. That means it's a TCP socket. And we bind this port number to this socket number, then listen. So here you can see this is one difference between the UDP and the TCP. So TCP is waiting for other client to come to this socket. And this one means the queue. So it means in this TCP socket, it does this three-way handshake with a queue size of 1. If there's more than one process that's waiting in the queue, it will just drop this connection. But this is not the number of connections that you can build. It can handle multiple connections. It can only handle the three-way handshake one at a time. So usually this is the number between 1 to 5. Then once it again enters the listening mode, then the server is ready to receive connection. Then again, this is an infinite loop. Then here, this is the socket program accepts the connection request from any client. When it accepts a request, then you will return a connection socket and the address. So this connection socket is actually different from the server socket. So in the example I mentioned before, usually a TCP server, there are two sockets. One is called a welcoming socket. So that is the server socket. The other one is the connection socket. That's what's returning here. Connection socket is only connected with one specific client. It's again, use the example of you go to a DMV. So you go to some window, you get a number, right? So you take that number and go to one window that provides service to you. You communicate with actually a clerk work with you. So this server socket is a welcoming desk. And this connection socket is actually the desk you actually work with this clerk to do the transaction. So this connection socket also already have the information of the client side address. You can just pass information to it. In this particular example, the server receives messages from this client. So again, this will receive 1024 bytes at a time. If there's a longer message, you can always come back to this, you write a for loop, keep receiving messages from this socket. Once it receives a message, then it decodes to a string, then return to this sentence, then turn that sentence to uppercase, then send that message back through this command, the send message. So again, you can see that when we receive a send message on the server side client, we don't need to specify the IP address of the other side, the other host, or the port number. It's because is already built into this connection. So after we are done with this transaction, we can close this. Okay, so this is the TCP server and client programs.
When using this protocol, how long do these TCP connections normally last? I mean, because it seems like you can leave it open for a long time.
Yes, it's a byte stream based. You can leave it for a long time as long as both sides agrees to this connection. If neither one calls closed, they can persist. So actually, that's a very good question. In the HTTP, you can actually do a persistent connection. That means you can just leave this open. Or you can do a non-persistent connection. That means you pass an object, then close it right away. The reason people do non-persistent connection is that if you want to pass 10 objects from the server to the client, you can actually build 10 different connections. So you send those packets at the same time.
If I were a malicious client, could I somehow like just open the connection and get it to start receiving but never send it anything and make it free?
Yes, that's a very good question. That's how you attack a website. So for example, this is how whenever there's something going on, people will you can download a malware. For example, if you hate CNN or Fox.com, you can just keep doing that. You can send a lot of connection to that server. Yeah, this server will be clogged, so you cannot serve other clients. Of course, there are a lot of defense against it. Like if you keep sending this request to send IP address, you'll just block your IP address. So that means you first need to control a botnet. That means you need to control many computers around the world. So they don't know which one is a legitimate user, which one is your box. Any other question here? Okay, so now actually we have about 10 minutes, so we'll do an exercise. If you cannot finish it, you should go home and then do that at home. Let me just go to. Let me explain these two exercises for you. So first, we're gonna do a TCP program. So what you can do is take the two program example I gave you, then think about how you can modify it. In this example we covered in the lecture, we control both the client side and the server side. But let's do something more fun. So for example, in the first one, let's write a server side program. And for the client, not just use your browser. You can use Firefox or Chrome as a browser. But then what you need to do is to write this server that accepts the input from a client and then print this line to the server's output. And then you can do this by modifying this program you provided. Then run your program on your computer. But now this is the server, right? So we need a client. So instead of writing our own client, you can just use any browser, but then direct to your server program. So now think about what's the IP address you should put into your browser's address bar. And also remember, you also need to put a port number. Like if you write a server program that's listening to the port 1000 or 8000, you need to tell your browser to go to this port number, right? And you can think about how do you specify that. So how do you know what is the IP address and the port number? Then your browser should send a GET request. So we'll talk about this in the next lecture about the HTTP. But it basically will send a message to your server. If your server is actually a legitimate web server, it should be able to parse this message and do something about it. But since you just created a dummy server here, all you will do is just display the message on the standout. So you can see that when you are writing a program, when you're trying to use your browser to visit a web server, what message actually is sending to that. So this is, here you are practicing writing a server program, right? So that's also can do the other way around. You can look at the GET request that you received from actually your real world browser. Then you can actually create a similar GET request. So this is basically the syntax, GET HTTP 1.1. Then this is a character and a return and a host. You can specify the IP address. Again, this is a return and new line. Then can you write a simple TCP client? Basically, you just send this GET request. What you need to do is just put this line, this string, into the message that you send into a program. So now, instead of writing your own server program, let's just use a real-world server program. So let's try www.ou.edu. So this is the server program that OU is running. So first, we need to know what's the IP address of this server, right? So you can type this pin, you can pin this server. Then your pin program will tell you what's the IP address. And then you can specify the IP address in your client program. And also remember, the web service also has use port 80. So now what you need to do is to find out, okay, what is this OU.edu server is sending back to you. So again, print out whatever message you receive on server and display it, and see if you can make sense of it. In this case, in both programs, I think I want you to get some experience. You are interacting with a real-world server. You are interacting with a real-world browser. So it's not a toy example. But in your actual program, it's actually very simple. You're basically sending messages and receiving messages. Since we're testing on using this HTTP protocol, as we mentioned before, you have to use the TCP protocol to communicate with this method. Okay, since we only have 5 minutes here, so I'll leave this exercise to you to work on this at home. So I'll change the due date, so you have more time to work on. And next time we'll come back and we'll practice how to run this, how to write this. We'll go over the answer together. Also remember, the other thing to remember is you already have the homework 1 assignment. Basically, in the homework 1, you are asked to write a server program, a client program. So in this lecture, we will cover this server program and client program. So now you should be able to ready to write the homework 1, problem 1. So this is due in about by the end of this month. When you look at the homework 1, you actually can see 2 days. There's a due date, so that is the due date. If you pass that due date, you will get a penalty. Then there's another day is called available until. That means this is a really hard deadline. So if you pass the due date by 1 day, you'll get a 10% penalty. You pass by 2 days, 20% penalty. If you pass at an available until date, that's the hard deadline, you will not be able to submit your homework. So make sure you submit it before the due date. Any other question about this exercise? Okay. So by the way, you can all run the server programs, right? So I uploaded the server and the client program on the Canvas. So make sure you install the Python module called a socket. Then first test it on your laptop. You can always create 2 terminals. One terminal runs the server program, the other terminal runs the client program. I will first make sure you can run the 2 examples we covered lecture first. Then go to the exercise and then homework.